This will be called the bouncing ball. And it's a good example of a typical kind of question that shows up. So, I'll write out the question. The ball is 70% efficient. If it is dropped from a height of 3 meters, how high will it bounce? Or how high will it go after the third bounce? Okay, I'm going to draw a picture to illustrate what's going on here. We have a certain initial height. I'm going to call that initial height, and then we'll put the ball right there. H0, I'm going to call it. I'm not going to call it 1 because I'll explain why in a minute. So the ball is going to fall downwards. Down it goes, down it goes, down it goes. Then it will bounce, and it will bounce back up again. But as we've seen, it will only go a certain height. And then it'll fall again, and it'll bounce back up again, but it'll only come up a certain height. And then it will fall again, and of course it will repeat this little sort of until it eventually fizzles out and stops. So this will be the level of the ground here, underneath. So initially, we'll call this initial position, we're going to call it position 0, because it's before the first bounce. Okay, this spot down here is bounce number 1. Here's bounce 2, and then bounce 3. We'll go that far because that's what the question is asking for, but you could keep going with bounce 4 and 5 and 6 if you wanted to. The number right here will be the height after the first bounce, H1. And then at this point we would have a height after the second bounce, H2, and then this would be the one after the third bounce, which is what the question is asking us to figure out. Okay? So the reason I started with 0 was so that this height number 1 would be the height after the first bounce. So the 1 stands for first bounce height. Okay? So that's the terminology that we'll use. To start off, we're going to look at what happens between 0 position and 1 position, the position after 1 bounce. All right? Let's do that by starting with our expression that the total energy in any one position has to be the same, well, I guess we can call it position 0, has to be the same as the total energy in any other position. But this is not quite correct. This would only be true if the ball was 100% efficient, but it's not. It says that the ball is 70% efficient, which means that the total energy after 1 bounce will not be the same as the energy that you started with, will it? There'll be some lost energy. So we have to figure out how we're going to write that. The way you write 70% is to use 0.7. That's the same thing. So somehow we have to put a 0.7 in this expression so we can make it a true statement. And this is where people often make the mistake. What they want to do is they want to put the 0.7 here because they feel like after the bounce is when it's 70%, right? But that would be incorrect, because what that would say in English is that the total energy that you started with right here is equal to 70% of the energy after the first bounce. That's not what we mean, it's backwards. So you have to be careful how you put that in. What we want to say is that in English we want to say the total energy after 1 bounce will be only 70% of what we started with. So the 7 has to go on this side. 0.7% or 70% of the total energy we started with will be what's left after one bounce. So you have to make sure you get this in the right place. Now the statement is correct. And we can use it now to describe the situation because we've incorporated the 0.7. Now let's look at the types of energy we have. In position 0, we have some MGH. So the total energy will be represented by this, and of course there would be 0.7 that we would carry down. At position 2, we also have MGH, and that's all, right? At the highest points of each of the bounces, the ball is actually not moving. So we have MGH, but it's a different H. It's the height at position 1. When you look at this, you can see that the MGHs can divide out of both sides of the equation, and that leaves us with 0.7 H0 equals H1. So far, so good. Now let's do that again for position 1 and position, what I'll call position 2, which is after the second bounce. And it's going to be exactly the same thing. The ball, after the next bounce, will lose another 70%, right? Every time it bounces, it's going to lose 70%. So 70% of the total energy, 70% of the total energy at position 1 then will become the energy total at position 2 after the second bounce. And again, we get 0.7 mg height at position 1, mg height at position 2. And again, the mg's cancel out, and we get another expression of 0.7 h1 is what h2 would be. The same idea. Now we can do the very same thing again for the third bounce. For the third bounce, we'll look at the comparison between position 2 and position 3. So we do 0.7 of the total energy at position 2. I keep writing that funny. Total energy, E total, at position 2 should equal the total energy at position 3, because each time we lose about 30%. So there's 0.7 times mgh2 equals mgh3. And again, we cancel out the mg by dividing it on both sides, and we get 0.7h2 equals h3. So we have these three equations. I'll circle them in green so we can pay attention to them right here. Now what we're going to do is we're going to put them all together. We're going to start with this third one. All right? So I'll write it over here. 0.7h2 equals h3. But if we look over here, h2 is the same as 0.7h1. So I'll substitute that, and I'll get this. I'll get 0.7 times the substitution, 0.7h1 equals h3. So the substitution, very straightforward. But h1 is equal to 0.7 of HO. So I can substitute this for h1. So then I would get 0.7 and 0.7, and then substitute 0.7h0 for h1 equals h3. And you can see what's happening. There's a pattern, right? For every bounce, we're multiplying by 0.7. So that pattern can be described mathematically with a very simple relationship. The height after any particular number of bounces, we'll use little n, so it could be after one bounce, or 2, or 3, or 4, or 5, or 7, or 1,000, will equal a certain percentage. I'll put a p there for a percentage, and look what's happening. We're multiplying that percentage repeatedly by itself, once for every bounce. So this would be p to the n. It's like an exponent, right? 0.7 cubed is what we actually have of each original. It's important, though, that you realize that this little p stands for the percentage of energy remaining in the ball, not the percentage of energy lost by the ball. And I'll show you an example in a minute that will clarify that. But this little expression is handy because it can tell us right away, without going through all these processes that we did, all three of these things, we can simply start with this, and we can find out how high the ball would go after so many bounces. So let's do our question and see what would happen. If we did Hn equals P n times HO, then the height after 3 bounces, which is what our question asked for, would be the percentage of energy remaining. If you're 70% efficient, that means you retain 70% of your energy. So 0.7. How many bounces? Well, it was 3 bounces, so we have to cube that. That's where the n comes in. And our original height was 3 meters. That 3 has nothing to do with the other 3s, it's just coincidence. And when you work this out, the answer comes to, I think, about 1.02-ish. Right? The height after the 3rd bounce. So you can get the answer quite simply. Now, the only way this could be different is sometimes a question will ask, instead of telling you how efficient the ball is, the question might say, a ball loses 20% of its energy on each bounce. Okay? And then it will say, find the height after 4 bounces, let's say. Find the height after 4 bounces. If you're losing 20% of your energy, how much are you retaining? 80%, which means the number we want will be 0.8 to put into here. So for this particular one, the height after 4 bounces would be 0.8 to the 4 multiplied by the original height, which I would have had to have given you. So let's say it starts at 6 meters high. And then you would put in the height after 4 bounces would be 0.8 to the 4 times 6, and then you can solve to get your answer. But you'll notice how we didn't just put the 20 in there. If it's losing, you have to do the little flip. You have to subtract from 100% to figure out how much is retained. So it's important to remember that the P, or the percentage you use, is the energy that's remaining or retained by the ball, not the energy lost. But otherwise, you can use this shortcut. So there's a question on your practice test that asks you to do this. Now you can do it very simply, instead of going through all that trouble from before. So I've given you this little shortcut formula. Now please don't fall prey to the idea that every time you see a question with a ball in it, this is what you use. This only works for a ball that's bouncing in these conditions, and you're trying to figure out a comparison between the initial height and the height after so many bounces. But there could be many bouncing ball questions that don't even relate to this at all. So don't think that this is for all questions with a ball in it. Otherwise, though, you can use it for these types of questions.